So in our next section, we're now going to look at the final configuration example of L3VPN. So how do we take the combination of the MPLS in the core, the PE to CE routing at the edge, the VPN v4 routing between the provider edge routers, and then combine this all together so we can have multiple customers at the edge, and we're keeping their traffic separate both from a control plane and a data plane point of view. Now, right now, I have the network reverted back to the case where we have ISIS running in the core. So ISIS is running between router 1, 2, and 3, XR 1, 2, and 3. And beyond this, we have pretty much nothing else configured. So one of the first steps is within the core of the network, we need to establish our IGP and LDP reachability. So IGP meaning we're going to enable OSPF on every single link, we're going to enable ISIS on every single link, and make sure that we can ping between the loopbacks of the provider edge routers. Now again, the reason that this is so important is that the loopback is going to be the next hop value that is advertised inside the BGP VPN v4 update. So if for some reason you cannot reach the loopback or you cannot reach the loopback through a label switch path, it means that you won't be able to actually forward traffic customer to customer. So before we go any further, before we even configure LDP, what we would want to do is go between the provider edge routers and make sure that we can reach their loopbacks. So let's say like on XR1's point of view, we want to make sure that we can ping 1111 when we're sourcing the packets from 11, 11, 11, 11. And that we can reach the other edge routers like 2222 when we're sourcing from 11, 11, 11, 11. And then also router 3 and XR3. So as it stands now, we pretty much have ISIS enabled on all interfaces, so this should not be an issue in reachability. Okay, but otherwise, this would be one of the first steps that you want to verify that if we can configure MPLS and L3VPN, what the problem is we want to avoid that we establish all the BGP sessions, we do the advertisements, we learn the updates from the customer point of view, but then we go to send the traffic and it doesn't go through. It makes it that much more difficult to try to track down where specifically along the label switch path did the traffic flow break. So you want to test this all individually before you go to the final solution. Okay, so first step is established that we have our basic IGP reachability. Next is we need to establish a label switch path. Now in this case we're going to be using LDP for the label switch path, but as I mentioned there are other labeling methods supported. So we could be using IPv4 unicast BGP plus labels, we could be using resource reservation protocol with MPLS traffic engineering, and we're going to come back to these in much more detail later once we establish the basic core reachability of L3VPN. Now in the vast majority of cases though, in real deployments, you would be using IGP plus LDP because the core of the network is already running IGP in order to get basic reachability. We simply add LDP on top of it, advertise labels for the loopbacks, and it means we have an any-to-any connectivity for the MPLS tunnels. Now specifically in this case, I'm simply going to enable LDP auto config, which again is going to enable LDP on all interfaces running routing. So under router ISIS1, we're going to say MPLS LDP auto config. On routers 1, 2, and 3, MPLS LDP auto config. And then on router 2, if we look at the show MPLS LDP neighbors, we should see that we have adjacencies with router 1 and router 3. From XR 1, 2, and 3, we're first going to turn the LDP process on. So globally, we say MPLS LDP. Then under router ISIS, we'll say under address family IPv4 unicast, we have MPLS LDP auto config. So same configuration on XR2 and 3. And then once we've established our LDP adjacencies, next thing we want to look at is, did we actually advertise the labels for the loopbacks in the IGP table? So again, we look at the show MPLS forwarding table, and we need to see for any of the /32s that we have label values that are associated with them. Again, the output that we are not looking for here is where it says the outgoing interface is either unlabeled or no label. That would mean that there's a break in LDP somewhere in the core. So we want to look at this everywhere on routers 1, 2, and 3. Let's look at the show MPLS forwarding table. Pipe include /32. And this should be all of the loopbacks. So pop label is okay, but unlabeled or no label is not. Show MPLS forwarding table, pipe include /32. Okay, looks good. Okay, so our first step is complete. IGP reachability is there, LDP labeling is there. Next step is that we're going to have the provider edge routers. So the provider edge routers are going to have the virtual routing and forwarding instance. This is going to go down to the customer links. We then will need to use those customer links to receive the routes in from them. So in this example, we're going to be using BGP routing, but later we'll come back and go through all the different variations. Okay, once we get the information from the customers, we then need to generate VPN v4 routes about these updates. So we're going to be doing iBGP peerings to the, that should say remote PE loopbacks. Okay, iBGP peerings to the remote BGP loopbacks. Okay, we'll see one of the keys with this is that when we do the peering, we need to make sure that this is going over the /32 loopbacks. We'll come back again later in later examples to talk about troubleshooting, but one of the common errors is that if you weren't peering to the /32 loopback, the MPLS label switch path is going to be broken. Okay, once we do the peering, and then we need to take whatever information we got from the customer and we need to redistribute it into VPN v4 BGP. Now, in our case, since we're going to be using BGP on the edge, we won't need to do an explicit redistribution statement, but we still will need to define our import and export policy, which controls the VPN membership of the individual routes. Okay, so next step is that we're going to have our virtual routing and forwarding instances. So specifically here, we're going to say that this is going to be a VRF-A on the left and VRF-A on the right. Then we'll have VRF-B on the top and VRF-B on the bottom. So on XR1, we're going to say that we have our two VRF definitions. We'll have VRF-A, which is running IPv4, and VRF-B, which is likewise running IPv4. We're going to say that the BGP network in the middle is going to be BGP AS1, and then on the edge here, we'll say that this is BGP AS4, 5, 6. We'll say this is AS10. This is AS7, and then this is AS8914. So we're going to run router BGP1. We'll say under VRF-A, we have our route distinguisher. We'll say the route distinguisher is 1:1. Under VRF-B, likewise, we're going to have route distinguisher 2:2. Now again, we'll see in more detail later that this distinguisher can be unique per customer or it can be unique per provider edge router. But again, the goal of this is that we're making the routes unique that are coming in from the CEs, coming in from the customers. Okay, if we look at the show config, we're going to need to do the same thing on XR3, but XR3 is not going to have both VRFs, it's only going to have VRF-B. So we'll say VRF-B globally is going to run address family IPv4 unicast, and then under BGP, we have the VRF configured. So router BGP1, we have the VRF. Okay, next step is we need to apply the VRFs to the interfaces. So before we do this again, we need to know what does the interface config look like, because we'll need to remove the IPv4, the IPv6 addressing, apply the VRF, and then reapply the addressing. Okay, in this case here on XR1, specifically these are interfaces gig 000411 and 811. So let's say do show run interface gig 0000 411 and 411 and 811. And to simplify this, we'll see that a lot of this, it's going to save you a lot of time to do these configs in Notepad. So what I'm going to do is to say the changes that we're making are to delete the IP addresses, to apply the VRF, so this is VRF-A, and then to reapply IP. Okay, same thing on the bottom. So that interface is going to be, we are removing IP, then we specify the VRF, and then we put IP back. And commit. Okay, next if we look at the show route, VRF-A, and show route for VRF-B, we should see those interfaces now moved from the global table into the VRF table. Now, it wouldn't hurt before we go beyond this is to make sure that we still have connectivity from the provider to the customer router. So in this case, we're going to ping in VRF-A, and destination is 10.4.11.4. We'll ping in VRF-B, 10.8.11.8. Because if we have some sort of basic layer 2, layer 3 reachability problem, we want to know about that now before we spend time troubleshooting MPLS or spend time troubleshooting BGP. Okay, so next, same thing we're going to do on XR3. So XR3 is enabling B on interface gig 00001314. So let's do show run on gig 00001314. On this interface, we say no IPv4 address, no IPv6 address. This is in VRF-B, and then we're reapplying IP. Okay, same step is now going to be true on the regular iOS routers. So from router 1, we're going to have VRF-A here. On router 2, we're going to have VRF-B. On router 7, we're going to have, or router 3, we're going to have VRF-A. So first on router 1, we're going to define the VRF. We'll say we have VRF definition A. Under address family IPv4, the route distinguisher is 1:1. Next, on the interface level, we need to apply the VRF. So we say VRF forwarding is A. Then reapply our IP address. For now, we're going to leave IPv6 alone. We'll come back and talk about this later within the scope of 6PE and 6VPE, which are for tunneling IPv6 traffic over the IPv4 MPLS core. Okay, so now if we do ping inside VRF-A to 10.155, we should still have reachability to router 5. Okay, from router 1, if we look at the show run VRF, basically the same config, we're going to put this on the other side, over on router 3. So we have VRF-A, do show run interface gig1.37. This is VRF forwarding A, and then we reapply our IPs. Okay, we're going to ping inside VRF-A 10.377. Okay, then lastly on router 2, we're going to have VRF-B. So we have VRF definition B. Address family is IPv4. The route distinguisher is 2:2. Interface is gig1.210. We have VRF forwarding B, and then we reapply the address. Okay, and then lastly, we're going to ping inside the VRF. Ping VRF B is 10.2.10.10. Okay, so now we have direct connectivity that's going to the customers. We're still going to have some sort of routing protocol that's going down to them. So again, in this case, we're going to be running this as a regular unicast BGP. So from router 2's point of view, we're going to say we're running BGP1. The address family is IPv4 VRF-B, and the peer is going to be 10.2.10.10. their AS is 10. From router 10's point of view, this is just going to be a normal peering. So we say router BGP 10, the neighbor is 10 to 10 to, remote AS is 1, and we'll say to redistribute connected. Okay, if we look at the show IP BGP summary from router 10's point of view, we have the peering up to router 2. From router 2's point of view, if we look at the show BGP IPv4, no, show BGP VPN v4 unicast for VRFB, we should see, let's say VRFB summary. We should see here in a minute that we start to receive updates in from 10. But at least at a minimum, we know that the control plane is built between the two of them, that we have the basic peering. Okay, so we'll come back to the rest of the BGP peers in a minute. That's going to be basically the final step to do the PE to CE routing. Okay, so we now have the VRFs configured. Next step is that we're going to run VPN v4 BGP. Now again, this is normal iBGP rules, so we could do a full mesh, we could do route reflection, we could do confederation, whatever structure that we have, as long as we advertise the updates between them, that's really all that we care about. Now in this example, to see both the iOS and the iOS XR syntax, I'm going to do route reflection similar to what we did before on both router 1 and XR1. So everyone's going to peer with router 1, everyone's going to peer with XR1. The exception, though, is that XR2 is not going to be running BGP because it doesn't have a direct link that's going to any of the customers. This is basically the P router that we're going to be tunneling the traffic over, and when we ultimately capture the traffic in the data plane and look at the Wireshark captures, we'll see what happens when XR2 receives it and how is it actually making its forwarding decision. So next on router 1, we're going to run the BGP process. So we'll say router BGP 1, and we're going to disable the activation of the IP version 4 unicast address family. Because we're no longer using BGP for global routing, we're using it just for MPLS layer 3 VPN. We'll say no BGP, default IPv4-unicast. Okay, we then define our peers. We'll say the neighbors are 2222, who is an AS1, 3333, (11, 11, 11, 11), and 13, 13, 13, 13. Okay, now each of these are going to be running VPN v4. So we're going to say the address family is VPN v4 unicast. And with some quick editing, we'll say that we're going to activate the neighbors. And then we're also going to specify that they are route reflector clients. And then also the neighbor update source is going to be the loopback. Update source is loopback 0. Okay, then the rest of this goes under address family, VPN v4, unicast. So again, we could have done some sort of template or peer grouping like we had done in previous examples, but the final result is that we have all of the BGP peers configured, we have them activated for this particular AFI, SAFI, and then we have them configured as route reflector clients. Now from everyone else over to router 1, we're going to do the same thing, except we just need to activate the one individual peer. So in terms of regular iOS syntax, this is going to look like this. We have BGP 1. We'll say no BGP default IPv4 unicast. The neighbor is going to be 1111. And then the neighbor is going to be activated. Okay, while we're at it, I'll also add 11 in there because that's the other route reflector. So neighbors are 1111 and 11, 11, 11, 11. Okay, this will be router 2 and router 3's config. Okay, now from XR1's config point of view, we're going to have the same thing. It's going to be a route reflector, and it's going to be reflecting to everyone else except XR2. So we'll say we have router BGP1. Our address family overall is going to be VPN v4 unicast. Okay, we're then going to have our neighbors. The neighbors are 1111. They're in remote AS1. The update source is loopback 0. And under address family VPN v4, they are a route reflector, route-reflector client. So if we show config, this is going to be the same thing for all the other neighbors, just we need to specify their additional addresses. So these neighbors will be there'll be 2222, 3333, and 13, 13, 13, 13. Okay, from XR2 and 3's point of view, if we show run router BGP, they're going to have a similar config to this, except they're not going to be route reflectors. So they'll have two neighbors. Their neighbors are specifically 1111 and then 11, 11, 11, 11. So as you can see how using a text editor is going to cut this amount of config down, or the amount of time that you're doing the config down, because it's a very templated type of design. The only thing that's really changing is going to be what are the neighbor addresses that we're defining. So on XR2 and 3. Okay, once this is accomplished, we want to check the status of the peerings everywhere. So in regular iOS, we would say show BGP, VPN v4, unicast, all summary. And we should see that we have all of the peerings up. Okay, that's on router 1, router 2, and on router 3. From XR's point of view, we're going to say show BGP, VPN v4, unicast, summary. Okay, in the case of iOS, all means all VRFs. So XR1 has all 4 of its peers. XR2 and 3 should be peering with router 1 and router 11 respectively. Actually, no, XR2 doesn't need to run BGP. Let's say rollback config last one. Okay, only XR3 is running BGP.